When we look at what we know about electromagnetism so far, we can see that there's a very strong symmetry between the electric fields and the magnetic fields. The electric fields are made by charges and they affect charges. The magnetic fields are made by moving charges and they affect moving charges. But there's something kind of odd about that. In particular, two people might not agree about whether the charges are moving or not. If I have a charge in my hand, I'm holding it completely still, I might think that that's not moving. But an ice skater going past would say that it is, because they would see it moving relative to them. Conversely, if they had a charge in their hand, they would say that that was still, and I would say that it was moving. And so it's a bit odd that we have things that affect only moving charges. So here I have a coil. It's a coil that goes around 400 times and it's connected to this ammeter. The ammeter measures current, so if any of these charges start moving around, we'll see, because we'll see that needle deflect. And the direction of the needle will tell us which way the current's going. Now there's lots of charges in there, but they're all still right now, because there's no current flowing, see? So they're all still, and so if I'm going to, here I've got a really lovely strong magnet, so if I want to make these things see the magnetic field, you think what I'd have to do is pick it up and have these charges moving. And you can see that if they move, we do indeed get a current. Okay, so here we have the coil and we have the magnet, and we know what the magnetic field lines do from a permanent magnet. They swirl up like this, and they swirl down like this, and they go all the way around to the other end. And we know what direction we were moving the coil. We're moving it sort of forwards and backwards. So let's just say we're coming closer at this time. Then we have a velocity going in that direction. And so if I want to look at electrons in this part of the coil, I can say I've got a magnetic field going up in this direction and a velocity going in this direction. So we want to find the direction of the force on that charged particle using the right-hand rule. So we put the fingers of our right hand in the direction of the v vector, and then we swing them round to the b, and then we look at our thumb, and our thumb is pointing in this direction, along the coil. Unfortunately, that's the direction for a positive charge, and an electron is a negative charge, so it's going to be going in the opposite direction. And so our force vector is actually going to be going that way along the coil. So there's our force vector. However, if all the electrons go in this direction around the coil, then actually what that means is that our current is going the other direction of the coil. So our current actually follows the direction of the right-hand rule because the current is defined as the movement of positive charge. So this magnet has no net charge, and so it has no electric field to speak of, and so there's no electric field to force those charges to move around in a circle and show up as a current. But it has a strong magnetic field, and when we move the charges by moving the coil, they do indeed experience a magnetic force which is going to make them go around the coil and show us a current. So we understood that. What we don't understand is why this works even when I move the magnet and not the coil. The reason we don't understand that is that we think that a magnetic field only affects moving charges. And that's right. Except we must be missing something about electromagnetism, because it shouldn't matter whether the coil's moving or whether the magnet's moving. And so there's something extra to learn about electromagnetism, and that was originally learned by Michael Faraday. So Faraday set up almost exactly this experiment, except instead of a permanent magnet here, he used an electromagnet. So instead of having one coil and a magnet, he had two coils, and one was attached to a battery and one was attached to an ammeter. And he found that he didn't get any current in the second coil when he just left the first coil sitting there, unsurprisingly. More surprisingly to him, when he connected the battery to the first coil and left it running, he also didn't see anything in the second coil, except for a little flicker when he first connected it. And then when he disconnected it, he got a little flicker again in the opposite direction. And so he was getting an electric field running around that loop only when he was changing the magnetic field that was going through that loop. And so Faraday's discovery of this process, which was called induction, so called because the changing current in one loop induced a current in the other loop. And it was James Maxwell and Oliver Heaviside who later went on to quantify that and really describe exactly what was going on. And it turns out that exactly what was going on was that it wasn't just the magnetic field, because the magnetic field is different at different points. So at different points throughout this entire loop, there's different magnetic fields. And even at different points of this coil, there might be different magnetic fields. And it turns out that what's important is not the field at a particular point, but the whole magnetic flux going through that loop. And we'll discuss exactly what that is in a minute. And the changing magnetic flux causes a force to act on the charges going around here, and this is an electric force, so we've got an electric field going around, And we know that if we have an electric field, that's a force per unit charge. And if charges go around at a certain distance, then they get a certain amount of energy per unit charge. And energy per unit charge is an electric potential. So we get another potential difference going around this loop based on the amount of changing magnetic flux we have.